Okay, so in part 2 of this lecture, I'm going to present a simple example just to show how sort of this one example, something strange happens, and there's a really cool application of stabilized embedding theorem that fixes some of these issues. So the example is just, there will be points on a grid in RD, right, in -1, 1D, right? So that inside the hypercube of D dimensions. Okay, so we take, say in 2 dimensions, we take maybe a grid like this. Okay, let's say this is 0, 0. Right, and now these are all the data points labeled and unlabeled, and now the labels we're going to have is point 0 is going to have the label 1. We'll have label 1. Right, and points x for which there are a distance to 0 bigger than 1, bigger or equal than 1, have label -1. Okay, so here you should think of this as having, here you're going to have label 1, and then there's a bunch of -1s up here, say. Right, and so on and so forth. Right, there's a picture, I have an image here that you can see. Right here, you see the point with label 1 in the center, and the points with label -1 at distance 1. Okay, so this is going to be our set. Okay. And now, we want to understand what happens when we try to label the whole circle. Right, the goal should be that, our function f somehow measures, right, distance to the center. In the sense that it should be close to 1 near the center, and then it should slowly go to -1. Okay, so we can now run the machine of machinery of semi-supervised learning and see what happens. This is exactly what I did here, right? And you see that it does exactly what we expect. Right? So, at 1 will be 1. Of course, at 0 will be 1, of course. Outside will be -1, and sort of slowly, or relatively slowly interpolating between the two. Okay, so this is sort of exactly what we would expect. Okay, so this is the one-dimensional version. Now, let's think about what would happen in RD, right? So let's go back, let's go to now the continuous problem. Right, so what we want really is a function f. Right now, instead of points in graphs and so on, I'm just going to think about functions in RD. Right, we want a function f from -1, 1D to R. Right, and what we want of this function is we want that f of 0 is 1, and f of x is equal to -1 if if the norm of x is bigger or equal than 1. Right, so if I think in 1 dimension, right, I have 0 here, and 1 and -1. Right, the function I'm looking for is something maybe a bit of this type. Right, I want it to be, let's say this is 1 and this is -1. Right, and I want it to be 1 here and then -1. Right, something like this. Right, this should be my function f, right? I want it sort of as smooth as possible in a certain sense. And so the natural thing to be would be, right, the equivalent in sort of Euclidean space analog would be to say that I want to have the norm of the gradient of f squared to be small. Right? This is sort of the corresponding thing to minimizing the sum of the differences squared. Right? And we saw even the relation between how this looked a bit like the quadratic form of Laplacian, and in fact, it is related to the quadratic form of Laplacian if we just take integration by parts. We saw this already. Okay. But now let's say that we take this in higher dimensions, right? In say 2, 3 dimensions. There are a lot, right? There are a lot more -1s than 1s, right? There's all these sort of, right, boundary of -1s, and there's only a little 1 in the center. And so potential fear is that the -1 sort of completely dominates. Right, and so in particular, it could be that the right solution is not quite this hat. So let me attempt to draw the hat in. So we have this. So here is 0, and here is 1, right, on the x-axis. Here, right, this would be the things of radius 1. So the labeled things is this needs to be -1, and this needs to be 1, right? So 1, -1. Now, another possible solution, of course, if we think that the -1 are going to propagate a lot more, could be for the hat to close a lot faster. Right? It could be that the hat does something like this in one dimension, which is a bit easier to see, or not maybe easier to draw. Right? It could correspond, instead of that picture over here, could correspond to something like this, for example. Right? And so, motivated by this, let's look at a specific function and see what will happen, right? So for now, we're just in a completely exploratory thing. So let's define this where, I mean, basically, this will be, right, this will be epsilon, and so we'll define f of epsilon of x to be the following, right? So it will be 1, so it will be 1 minus 2 norm of x epsilon if the norm of x is smaller than epsilon, and -1 otherwise. Okay, so this is basically this hat, right? This hat with radius epsilon here. Right? Why? Because if I take x to be 0, then this is just 1. If I take x to be 1, right, then the norm of x is bigger than epsilon, so I get -1. Right? And so now let's look at what is the norm of the gradient squared. The integral, right? Of course, here I need to integrate, right? It can't just be the norm, it needs to be some kind of integral of the norm. So let's look at what is the integral, right, in the ball. Now I'm going to do everything very, very handily. So what is this? Well, first of all, the integral, right? So let's see. Let's keep things quite hand-wavy. Then the integral, right? There's no change basically when, I mean, the function and the way I define it is not quite integrated, like it doesn't integrate everywhere, but let's keep things quite hand-wavy. You can make this all much more precise. Then essentially outside of the ball of radius epsilon, there's no derivative. And inside the ball of radius epsilon, the derivative is of order 1 over epsilon, right? This is sort of the slope is of order 1 over epsilon. So this means that I just have to integrate on the ball of radius epsilon, right? And the value is roughly, the gradient is roughly 1 over epsilon, so I get roughly 1 over epsilon squared, right? Because I have the gradient squared. But now all this is just now the volume, right? Because this is constant, this is just the volume of the ball over epsilon squared. Now if we think about what this is, right? The order of this, the volume in the dimensions of something with radius epsilon, right, is just epsilon to the d, right? So this will be in the order of epsilon to the d divided by epsilon squared. So this will be in the order of epsilon to the d minus 2. So in particular, there is a problem there because, right, so let me write in another color here. Right, right, so we have that, you know, this gives something like epsilon d minus 2. So in particular, if d is 3, right, if we're in 3 dimensions, then the value of this, right, epsilon of d minus 2, this is actually going to 0, right, as epsilon goes to 0. Right, meaning that the optimal solution is just to take, you know, at least among this type of hats, is just to take the hat arbitrarily small, right? Which means that we're really not learning. You know, this label is just being completely ignored, and we're really not learning about it. Okay, so let's run an experiment to see if this actually is the case and what it is that we see. Okay, so we have this experiment here where we take right. So we do this first in 1 dimension, right? So in 1 dimension we get right, we get our the labeled data. So there's a 1 in 0 and the -1 at the points at distance 1. And now we can see what happens when we run semi-supervised learning. Exactly this algorithm, and interpolates very nicely. We get exactly a very nice, very nice interpolation between 1 in the center and the -1s on the outside. Right. So now, of course, we saw already the example in dimension 2, right? So in dimension 2, we start with 1 in the center, -1 on the outside. And we see that, if we run semi-supervised learning, it interpolates maybe not quite as nicely as it still doesn't do quite as nicely as one dimension, but it's still interpolating. Right? But now let's look at what happens in 3 dimensions. Okay, so here's the same experiment done with in 3 dimensions. Right. So what we do here is we just do the exact same thing on a grid on 3 dimensions. It's a bit harder to represent, but you can see here what was done. There's a 1 in the very center, somewhere over here. There's a little yellow here that you can see. And then there's -1s in everything at distance 1, right? So everything at distance 1 from that center gets a -1. And now we can run. Right now we can run semi-supervised learning and see what happens. Right? And if you see, essentially, all the information is gone about the center. Right? You just get the 1 in the center, and almost everything else gets a -1. Right? It's exactly what we're seeing is exactly sort of this. Right? That at least among these solutions, you can get the gradient to go arbitrarily close to 0, the integral of the gradient, which somehow corresponds to the quadratic form of Laplacian, by just taking this hat thinner and thinner and thinner, and this is sort of exactly what the computer is doing, right? I mean, it's very much exactly what the computer is doing. Of course, here, right, what we're doing here is not exactly the same as RD because it's a grid and so on, but we see already that what we're deriving in Euclidean space is happening exactly there. And so the question is, how do we fix this issue? Right, so, if we're dealing with some data set, it could be that in a particular example of, say, an X-ray and having a disease or not, right? It could be an example where it's a rare disease and actually very few of the X-rays have positive, but there's actually a lot of them with negative. And so we can't just sort of ignore the one with the 1, just because there's a lot more -1s, right? And this is where this approach, this semi-supervised learning approach, sort of fails a bit, because in some of these cases, it will just, if there's very few labels with one value, we'll just fully ignore them, essentially, almost, right, as we see in this experiment. But so how can we fix this? And one way to fix this is by using Sobolev's embedding theorem, or not quite by using Sobolev's embedding theorem, but by being motivated or inspired by Sobolev's embedding theorem. So I will not actually write all of Sobolev's embedding theorem here, but I'll just say that Sobolev's embedding theorem, so Sobolev, this is important to study, functional spaces that are important in differential equations, right? Embedding theorem, right? Among other things, what it says is if the dimension that we're in, so the function lives okay, let me say m is bigger than d over 2, where d, so f, let's say we have a function f that takes values that is, that lives in d dimensions, right? So f is a function in Rd, right? If m is bigger or equal than d over 2, then we know that if f is inside hm of Rd, then f is continuous, or essentially continuous. And how do we? So what does this statement mean? That if f belongs to this space, then f is continuous. Essentially, it says that if f is a function in d dimensions, let's say that f is a function from Rd to R. Right? That the space hm of Rd is a space of functions whose derivatives are square integrable. right? Essentially, I mean, they could be the weak derivatives because it's okay if the derivative is not defined exactly everywhere, so that I don't want to get into all of that. They're essentially the space of functions like f. If f is here, it means that f has a square integrable first derivatives. Or n derivatives in this case because it's n. So in particular, because what we're doing, right? Because what we're doing is we're making sure that the gradient f squared is small, right? We know for sure that f should, right? Our f naturally should belong in each one of our d, right? Because I mean, we're forcing for sure its first derivative should be square integrable because this is even what we're optimizing for, what we're minimizing. And so in particular, right, it means that, you know, but for 3, if d is equal to 3, say, then, you know, m1 is not bigger than 3 halves, right? And this is why we're seeing what we're seeing here in the computer. Now, of course, what would be one way to fix this? If we're stuck in 3 dimensions, if we're stuck with d equals 3, then what we could do is try to make sure that f is inside H2 of R3, right? Because indeed, well, even though 1 is not bigger than 2/3, 2 is bigger than 1 is not bigger than 3 halves, 2 is bigger than 3 halves, right? So if somehow we can force the second derivatives of f to be square integrable, then we should be okay, right? And so, okay, let me do it here. So what's the idea? What does this motivate? And you know, I'm being extremely hand-wavy through this, but in the lecture notes that I have, you can see references to papers where this is done properly. But I just want to highlight how you can use like a cool theorem from functional analysis to motivate an algorithm, to motivate a fix for a problem that we see in data. And so, right, we somehow want to ask, right? So the idea is instead of imposing just that the derivatives are small, we somehow want to make sure or want to promote small higher order derivatives. Okay. So it turns out one thing we can do that essentially corresponds to making sure that second order derivatives are small is instead of minimizing, instead of how we're doing, minimizing over, of course, a few f transpose Laplacian f, we can minimize the Laplacian squared. Right? This, in some sense, corresponds to imposing that higher order derivatives are small, right? Sort of corresponds to them equals 2. Right, so let's do exactly that. So I do exactly all the same on the computer, just when I solve for a few, instead of minimizing with the Laplacian, I do it with the Laplacian squared. Right, so same thing, I'm just minimizing this now. Right, and let's see what happens. Right, and we get a much nicer picture. Right, it's much smoother. It sees the center. Right, the propagation of the one goes much further. Right, and it's really learning what we would think maybe is the right geometry of this. And so, in this paper that I cited the references that made this observation first, they have ways of with like data sets and so on of telling how high of derivatives you should go to and how it differs when you do different ones and so on. But the message here that I want to give is one, there's a very simple way of doing semi-supervised learning that uses the same objects that we studied before, the Laplacian and so on. And when faced with an issue like very little data of one type versus the other on the labels, then sometimes cool like theorems that seem very much just in the realm of not in the realm of graphs for sure. So like embedding theorem, right, is used. in applied math for things related to differential equations, but definitely not on graphs, can actually give you quite a bit of insight. And motivated by it, you can fix this in a way that I would argue would not be, intuitive. Without the motivation from that, I would not think of taking L square to try to solve this issue. And so now we'll move to actually, right? So this finishes graphs, and we're going to move into matrix concentration next. All right. Thank you.